All right, gang, Math 5500. Going to try something new. I'm editing some of my videos for 5500 because they need it. And I found that, when I first started teaching online courses, I had a lot to learn. You might say, well, you still have a lot to learn, but what I tried to do back then is I tried to keep my online videos and instructional videos as close to my face-to-face lectures as possible. So what I would do in a classroom, what I think maybe most of you do when you teach, if you're a teacher, is go to the board and just start teaching. But I found that there's a missing part to that in the instructional videos is we need to keep them as brief as possible. That way you're more likely to watch them. So instead of writing everything else out as I teach, I've already written it out, and the reason is I want to try to make the videos shorter. You might say, well, Dr. Darbo, you can make them shorter if you don't go into this long-winded introduction. Sorry. The topic at hand in this video is called least squares. Now, before we get into least squares, I want you to just step back and review the difference in the notation. When we have y equal our model beta 0 plus beta 1 exabyte plus an error term, we have to include the error term because when we put the x value into our model, very, very, very unlikely that we're going to that's going to be equal to the corresponding y. So there has to be an error term. When there's no error term, we're actually doing a prediction. It's fine to put in an x value into our model and get out a predicted value. We don't need an error term there. So I noticed that at this stage, a lot of students confuse y sub I and y hat sub I. And I'm assuming it's because I haven't taught it well enough. So that's the reason for that. Now, let's go into bigger, better. Well, it's not bigger, better. It's just different. We think about our population model. So we have to think that of all of our data, x sub I comma y sub I, we have a model that represents the entire population. But in the spirit of inference, we typically don't have the luxury of dealing with all of the data in our population. So what we do is we take a sample, and from the sample we create beta estimates. So beta 1 is going to be estimated by B1 or beta 1 hat. Beta 0 is going to be estimated by B0 or beta 0 hat. Same thing we do in introductory statistics. If we have an unknown population mean, we're going to estimate that using x bar. If we have an unknown population mean difference, mu1 minus mu2, we're going to estimate that using x bar 1 minus x bar 2. Now, the topic at hand is least squares. And it's one of the most misunderstood concepts when I teach this class. And it shouldn't be. And that tells me that I just need to improve my instruction. So for least squares, sorry, my daughters are home doing remote learning, and so they're doing their thing, I'm doing mine. So we have our data set, x1, y1, and x2, y2, and so on. And we have a relationship. So we can look at a scatter plot, get an idea of a relationship. Next step is we fit a model. So we get our beta estimates, B0, B1, right? And we call this the line of best fit. Now, to find the B0 and find the B1, we typically use technology. Use R, SPSS, JUMP, whatever it may be. And we can also find out later in the class that we can create these values using matrix operations. Another way of looking at the theoretical foundation is to look at the least squares approach. Now, gang, the least squares approach is is two parts. The squares part is just the error squared, so it's the residual, it's the observed y minus the predicted y squared, and the least part of that says that we're going to minimize that. So we know that y hat sub I is the same thing as b0 plus b1 x sub I, right? So by substitution, we get the equivalent expression. From there, we're going to create a Q, which is going to be the sum of these deviations squared over our entire data set. So guys, the goal is going to be able to find the value for B1 and B0, excuse me, that minimizes the sum. So let's step back from this just a second. The least squares approach, when you see that on an exam, when you see it on an assignment, whatever sort of assessment it may be, you're going to think three steps. You're going to create your Q, you're going to take the derivative, you're going to set the derivative equal to 0, and you're going to solve. Now, why do we set the derivative, take the derivative? Well, guys, think back to Calc 1. If you were going to find a minimum value for this function, what would you do? Well, you take the derivative, right? You take the derivative and set it equal to 0 because we know that the slope of that tangent line has to be 0 at this minimum value. So again, it's really nothing more than you already know how to do. It's just in a different context. Now, let's look at just a very, very, very simple illustration. So I chose a small data set, and although we typically don't begin with a guess, let's just say that we are making a guess. All right. Now, what I did is I just went ahead and graphed this on the calculator, and I think it's a reasonable guess, right? I mean, it goes through this kind of the central focus of our the pattern of data. It seems to kind of balance out the differences between our observed data and the predicted data, being on the line. So I think it's reasonable. Well, what we can do from this is we can calculate our Q. So we have our sum from I equal 1 to 3 because we have 3 data points. And then, of course, our beta hat is, our y hat is just by substituting our model. So y minus y hat squared. Well, if we run through, the first term has x value 1, y value 1. The next term has x value 2, y value 1. And the last term has x value 3, y value 3. Simple arithmetic, sum all that up, we have 2.125 is the Q value. Now, is this the lowest value for Q? You can imagine the insanity if you tried to select all the reasonable models. Well, you couldn't because there's infinitely many. So what we do is we inject a little bit of theory here, and we're going to generalize the approach as follows. So, sum from 1 to 3, again, 3 data points. But now what we're going to do is we're going to assume that B0 and B1 are unknown. We're not assuming it, they are unknown. We're trying to find the B0 and B1 that minimize Q. So again, insert X1, Y1, X2, Y2, and X3, Y3. Little bit of simplification leads us to this. Now, guys, you don't want to, I guess you could go ahead and expand all this, but you really don't need to. Just use the chain rule. And so the first expression, first term, use the chain rule. So 2 times this quantity times the derivative of the inside part with respect to B0, we would have a -1. So that's the reason for the change in signs. So each of these terms has the following derivative. Now, guys, we have to use the partial here because we're taking the partial of Q with respect to B0 and the partial of Q with respect to B1 because we have 2 things that we're actually solving for. So I went ahead, I didn't want to waste your time here, again, in the spirit of making the instructional video as brief as possible. I encourage you to try it out. I made a silly typo here. It wasn't a typo, I did a silly arithmetic mistake. I did 2 plus 2 plus 2 No, I'm sorry, I did 2 times 2 times 2 and got 6. When it should have been 8, so it changes this to 28 instead of 26. So I would highly encourage you to take the partial of this with respect to B1 and check that we get the same thing. I think you'll find out that we do, unless you make a silly arithmetic error like I did. Now the next step is once we have the 0, we're going to set each one of those equal to 0. So we're going to solve simultaneously. And again, put in the correct value. It's strange how that works better that way. And so this is equivalent matrix form. And create the matrices. And you can see that we get the solution negative 1/3, 1. So that's our solution for B0, B1. So B0 is negative 1/3, B1 is positive 1. Let me get out of here and show you how you could do that in R. It's kind of clever. It's going to set the stage for something we'll do a little bit later. What I would do, first of all, is just create the first matrix, or the entries of the first matrix. Reading from first row to second row. And I'm just going to call the other matrix Y for the lack of anything better. What was it, 10, 24? All right, so I'm going to create a capital X matrix using the matrix. So I want to use lowercase or lower x. So I want the in row to be equal to 2, in column to be equal to 2, and by row equal true. Now what this does is it creates my matrix using this dimension by row. So it's going to read across the row to create this matrix. There's going to be situations later on where we do by row equal false, and that's if we have a vector from a data set, but more about that later. All right, and you can see when I do X, I get the matrix that I want. Y is just going to be another matrix, but using the Y entries. So in row equal 2, in column equal 1, and by row equal true. All right, so Y, we get that. Now, if you think what we need, because we have our X matrix times our beta matrix, B0, B1, equal 1024, we need to take the inverse of the left matrix. So we do that in R using solve. So I want to solve X, not really solving it. Again, solve is just taking the inverse. When we multiply two matrices, we have to do percentage time percentage and Y. Well, when you do that, you see that we get the 2 by 1 matrix for beta, which is negative 1/3, positive 1. All right. So y hat equal 1/3 plus x will produce the minimum value for q. That's our least squares. And when you actually calculate your q value, and again, check this out. I'm pretty sure it's correct unless I did something arithmetically foolish, but I don't think I did. The q value is equal to 2, which is lower than the 2.125 that we got earlier with what I would call a reasonable guess. All right, gang, again, attempting to keep videos shorter, briefer. So I think that's all I'm going to do in this video. All right, take care.